Welcome back to Equilibrium. In part 3 of this unit, we're going to be talking about Kp, different from Kc that we looked at last time, heterogeneous equilibrium, and the reaction quotient, otherwise known as Q. Let's get started. Kp is the equilibrium constant based on the pressures of the gaseous products and reactants rather than the concentrations. The formula for Kp is exactly the same as it is for Kc. The only difference is you're going to see parentheses here instead of brackets because we're not talking about concentration. And you'll see this little P here, which means pressure. So the pressure of the products raised to the power of their coefficients divided by the pressure of the reactants raised to the power of their coefficients instead of the concentration. In order to switch between Kp and Kc, our formula Kp is equal to Kc times RT to the delta N. Delta N, that's the change in moles, the moles of a gas specifically because gases are affected by pressure and liquids and solids and solutions are not. So that's products minus reactants. Let's see. Products minus reactants. All right, let's see an example of what I'm talking about. Given NaCl makes NO plus Cl2, at equilibrium the pressures are NaCl is 1.2, NO is 0.05, and Cl2, that should be a Cl2, is 0.3 atmospheres. So calculate Kp. So we're going to write the equilibrium constant expression exactly the same way that we did with Kc. That is the pressure of NO, because that's a product, squared times the pressure of Cl2 divided by the pressure of NoCl squared. So the only difference here is we're indicating that it's pressure, not concentration. So parentheses and a P rather than brackets. Then I'm going to plug the numbers in that I'm given. So the pressure of NO was 0.05. and that guy was squared. The pressure of Cl2 was 0.3, and the pressure of NoCl was 1.2, and that one was also squared. So I'm going to get out my calculator. 0.05 squared times 0.3, 7.5 times 10 to the negative 4. 1.2 squared, 1.44. So let's divide those numbers, and I end up with 5.21 times 10 to the negative 4. So that is my Kp. Now Kp is different from Kc because it relates to pressures instead of concentrations, but we can convert back and forth between them. Remember that. Kp is equal to Kc times RT to the delta N. So plugging in what we know, 5.21 times 10 to the negative 4 is equal to Kc. That's what we're solving for. Okay, so R, that's the gas law constant. That's 0.0821 liters atmospheres per kmol times T. At this case, it doesn't tell me what my temperature is. Never mind, it does. 25 degrees, so that's 298 K. And then to the power of delta N. So over here on the product side, there are 3 moles of gases. If we look on the reactant side, there's 2 moles of gases. So if I do products minus reactants, that's 3 minus 2, I'm going to raise this to the power of positive 1. So when you're mathing this, when you're typing this in your calculator, it's 0.0821 times 298 and all of that raised to the power of 1 before you multiply times Kc. So simplifying, I end up with 5.21 times 10 to the negative 4 equals Kc times, let's type that in, 24.5. And so now I'm going to divide both sides by 24.5, and I end up with Kc is equal to 2.13 times 10 to the negative 5. So that's the relationship between Kp and Kc. Look at heterogeneous equilibrium. Remember that heterogeneous means that things are different. They're not all the same. And in this case, they're not all gases or they're not all solutions. There might be gases and solids and liquids all in one reaction. So only gaseous or aqueous solutions can be included in the equilibrium constant expression. This is a really important thing that you just got to remember. Solids and pure liquids cannot because their concentrations don't change throughout a reaction. A solid can dissolve, but the solid that remains will still have the same concentration as the solid at the beginning. So solids and liquids are completely ignored when writing the K equals expression. So if I'm going to look at this reaction, CaCO3 solid makes CaO solid plus CO2 gas, and I'm given the K. Remember when it doesn't say what K it is, that's assumed to be Kc instead of Kp. It's just assumed. So let's write the equilibrium constant expression for this reaction. Because before I can find any concentrations, I need an equation to plug it into. So we're looking for products. In this case, the only product that's not a solid or a liquid is CO2. So bracket CO2, because I'm talking about the concentration of CO2. And then CaO I can ignore because it's a solid. CaCO3 I can ignore because it's a solid. So Kc is just equal to CO2, and that's it. The concentration of CO2 is the same as Kc, 8 times 10 to the negative 3. The only difference is now it has a unit. When it turns into a concentration and not a K, the unit is molarity. So let's calculate Kp. Kp is equal to Kc times RT to the delta N. So Kc is 8 times 10 to the negative 3. And then RT is 0.0821 times 750 degrees Celsius. Let's see. We got 1023. And then to the power of delta N. So this is 1 mole of gas. And then on the reactant side, 0 moles. Products 1 minus reactant 0 is 1. So 1023 times 0.0821 is 83.988, so 84 times 8 times 10 to the negative 3. And when I type that in, I end up with 0.67. And because it's a K, even though it's Kp, there is no unit, just 0.67. That's my final answer. So how many moles of CaO are produced in this reaction? Well, I can tell from the balanced equation that CaO is in a 1-to-1 ratio with CO2. For every 1 mole of CaO that's produced, 1 mole of CO2 is produced. CaO to CO2 is 1-to-1. So all we have to do is figure out how many moles of CO2 are produced in this reaction, so that then we can know how many moles of CaO are produced in this reaction. And good thing we already have the concentration of CO2. So that's 8 times 10 to the negative 3rd molar, and it's in a 5-liter flask. So to find the number of moles, I'm going to multiply 8 times 10 to the negative 3rd times 5, and I end up with x is equal to 0.04 moles. So since 0.04 moles of CO2 are produced, that means that 0.04 moles of CaO are produced. CO2 means 0.04 moles of CaO because of the 1-to-1 ratio in the balanced equation. Now let's look at the reaction quotient, otherwise known as Q. If the concentrations of reactants and products other than those at equilibrium are placed in the K expression, the result is known as the reaction quotient, or Q. So if Q and K are the same thing, the system is at equilibrium. If Q is greater than K, the system will shift left to achieve equilibrium, making more reactants. And if Q is less than K, the system will shift right to achieve equilibrium, making more products. So the formula for Q and the formula for K are the exact same thing. Because they are the exact same thing, it's just that Q can be the anytime constant when K is the equilibrium constant. So the formula is products raised to the power of their coefficients divided by reactants raised to the power of their coefficients. This would be QC. You could also have QP, which is the pressure of the products raised to their coefficients divided by the pressure of the reactants raised to their coefficients, if you're talking about QP instead. Example. Given A plus B makes C, K is equal to 8 at 25. The initial concentrations, like at the beginning when I started the reaction, I had 2 moles of A, 2 moles of B, 10 moles of C in a 1 liter container. If this reaction is this reaction at equilibrium? So first I want to write the equilibrium constant expression, but in this case I'm going to call it the reaction quotient expression because I don't have equilibrium numbers, I have initial numbers. So my products divided by my reactants raised to the power of their coefficients, but they're all 1. So I'm going to plug them in. 10 divided by 2 times 2. 10 over 4 is 2.5. Okay, so now we're going to compare Q to K. Notice that Q is less than K because Q is 2.5 and K is 8. So if Q is less than K, that tells me that the system is going to shift right to make more products. So if we think about it this way, I want to make the fraction 2.5 over 1 to equal to 8 over 1. And if my formula is products divided by reactants, in order to get from 2.5 to 8, I'm going to have to increase the top number in this fraction and leave the bottom number the same. So I'm going to have to make my reaction shift towards the right to get more of those products so that the ratio will come to be an 8 over 1 instead of a 2.5 over 1. Here's another example. Predict the direction the reaction will proceed toward equilibrium if the following initial concentrations are given. So first thing I need is a K expression or a Q expression. They are the same thing in these circumstances. So we have SO3 squared over SO2 squared times O2. So now I'm going to plug in what I have. SO3 is, I did that wrong, 0.2 squared. SO2 is 0.2, also squared times 0.2. Well, that makes life simple. So 0.2 squared divided by 0.2 squared times 0.2 is 5. So now we're going to look at Q compared to K. Q is 5, which is less than K, which is 13. So if I were going to try to get from 5 over 1 to 13 over 1, I would have to increase the products, so I would have to make my reaction shift right. Okay, so try the next one on your own. Pause the video now. Well, hopefully you did that. We've got the same Q expression as we had before, so I'm just going to jump straight into plugging in the numbers. 0.2 squared over 0.121 squared times 0.21. So I end up with 13. Hey, check that out. Q and K are the same thing. Since Q and K are the same thing, I don't have to shift in any direction to get to equilibrium. It's already at equilibrium. There's going to be no shift. Everything is copacetic. So now I've got QP instead of QC. This is the same exact reaction, except this time I'm going to be using gases and pressures instead of concentrations. So my QP will look identical to the one that I just did, except that I'm going to use pressures instead of concentrations. You have to watch out when the College Board asks you for a QP or a KP that you do not use brackets, which indicates concentration, but you have to use the capital P with a subscript of whatever substance you're looking for. So same formula, the pressure of SO3 is 0.2 atmospheres squared. The pressure of SO2 is 0.1 squared, and O2 is 0.2 not squared. 0.2 squared over 0.1 squared over 0.2 is 20. So indicate the direction in which the reaction will proceed towards equilibrium. 20 is greater than 0.14. So if I was thinking about this in fraction terms, 20 over 1 to 0.14 over 1, and it has to get from the Q to the K because it's trying to get towards equilibrium, then I'm going to have to lower the products. I'm going to have to make this top number come down. And the only way to lower the products is to get the reaction to shift away from the products. Shift left towards reactants. And that way Q can get to be equal to K. All right, we've got one more, and this one I want you to try to work on your own. Pause it here. I think you can do this. Okay, well, hopefully you tried. First thing we're going to do with this reaction is write the equilibrium constant expression. So K is equal to HF squared over H2 times F2. Calculate the initial concentrations. Notice that this is in a 5-liter flask, so the concentration of HF is 5 moles divided by 5 liters, which is 1. Concentration of H2 is 0.5 moles divided by 5 liters, which is 0.1. And the concentration of F2 is 0.75 moles divided by 5 liters, which is 0.15 m. So the next thing is we're going to calculate Q and determine in which direction the reaction is going to shift. So the Q expression and the K expression are the same expression. I've got HF squared, that's going to be 1 squared, divided by H2, which is 0.1. That one's not squared, and then F2, which is 0.15. So 1 squared over 0.1 over 0.15 ends up with 66.7. Let's round that. So if Q is 66.7, that is much greater than K, which is 0.01. So since Q is much greater than K, I'm going to have to lower Q, or lower the products, in order to get Q to equal K. So I'm going to have to shift left towards the products, the reactants, in order to lower the reactants and make the ratio 66.7 over 1 closer to 0.01 over 1. All right, well, that's Q. Hope we see you next time for Le Chatelier's principle.